Let's say we have a function u equals to f of x comma y, where x is a function of s and t, and y is also a function of s and t. And very often we have the need to change the expressions containing the terms x, u, x, y, dou u by dou x, and dou u by dou y to expressions involving the terms u, s, t, dou u by dou s, and dou u by dou t. For this change of variables, we need a formula. So before I tell you how we get this formula, let's recap a little bit of what we learned in total derivatives. So in total derivatives, we learned that let's say they give us a function u equals to f of x comma y, where x is a function of t and y is a function of t. First, using the dependency graph, we get that u depends on x and y, and x depends on t, and y also depends on t. So using chain rule, we get that du by dt equals to dou u by dou x into dx by dt plus dou u by dou y into dy by dt. Now using the same chain rule, we are going to find out dou u by dou s and dou u by dou t. Now how do we find these two? So for this functions, we have a dependency graph that looks somewhat like this. So u depends on x and y, x depends on s and t, y also depends on s and t. So if I were to find out dou u by dou s, and mind you, this is dou u by dou s, it's partial differentiation, not ordinary differentiation. Why? Because here x only depends on one variable, so we can use direct normal differentiation, but here x depends on two variables, and we learned that in functions which have two or more variables, we use partial differentiations. So if I'm partially differentiating it with respect to s, t is considered as constant. So considering t as constant here, what are the pathways to get from u to x? We have this as our first pathway, so that would be dou u by dou x into dou x by dou s plus dou u by dou y into dou y by dou s. Similarly, for dou u by dou t, we get dou u by dou x into dou x by dou t plus dou u by dou y into dou y by dou t. Now solving these two equations as simultaneous equations of the terms dou u by dou x and dou u by dou y, or here as well, we get the values in the terms of u, s, t, dou u by dou s, and dou u by dou t, which is what we wanted. So these two formulae help us to change the variables, and also repeated application of these two formulae gives us higher derivatives of the function u. So let's do a problem. So this is our given problem. So z is a function of x and y. We have a relation of x in terms of u and v, and also y in terms of u and v, and they asked us to prove this. So our dependency graph is z depends on x and y, and x depends on u and v, y also depends on u and v. So dou z by dou u, as we saw before, this is one of our pathway to reach from z to u. So that is dou z by dou x into dou x by dou u plus dou z by dou y into dou y by dou u. Dou z by dou x, we don't really have anything to solve there, so we write it as it is. And now differentiate this equation with respect to u. So that would mean v is constant. So this equation, if we're differentiating it with respect to u, we get e power u will be e power u plus 0. So that is e power u plus dou z by dou y into this equation with respect to u. Differentiation of e power minus u would be minus of e power minus u minus 0 again. So minus of e power minus u, that would be equation 1. Similarly, dou z by dou v would be dou z by dou x into dou x by dou v plus dou z by dou y into dou y by dou v. We write this as it is, and this equation with respect to v So dou x by dou v equals to u is treated as constant, so that is 0 plus minus of e power minus v. So that is minus e power minus v plus dou z by dou y into dy by dv. So we're differentiating this equation with respect to v. We get dy by dv equals to u is constant, so that is 0 minus e power v with respect to v is e power v, and we get e power v. That is equation 2. Now equation 1 minus 2 would be dou z by dou u minus dou z by dou v equals to dou z by dou x e power u plus dou z by dou y minus e power minus u, and this whole thing minus dou z by dou x e power minus v minus plus dou z by dou y minus e power v. This negative they get cancelled, so gonna take dz by dx as common. We'd get e power u plus e power minus v minus dz by dy as common. We'd get e power minus u. Oh, pardon me, dy by dv is minus e power v, so we have a negative here and there's a negative here as well. These negative get cancelled, so we're taking minus dz by minus dou z by dou y as common. We get e power minus u plus e power v. This is nothing but x and this is nothing but y, so that gives us x dou z by dou x minus dou z by dou y into y, which is what they asked us to prove. So let's solve another problem. So u is a function of r, s and t, and where r is a function of x and y, s depends on y and z, and t depends on z and x. So let's find out du by dx. Dou u by dou r into dou r by dou x plus dou u by dou t into dou t by dou x. So dou u by dou r, we leave it as it is. Of this equation, if I'm partially differentiating it with respect to x, y is going to be constant. So we get 1 by y plus dou u by dou t and dou t by dou x. We are partially differentiating this equation with respect to x. So z is going to be constant. Derivative of 1 by x is minus 1 by x square, and z is a constant, so we're going to write it over here. This is equation 1. Similarly, we're going to find dou u by dou y, and these two are our paths, so we're going to get dou u by dou r into dou r by dou y. That gives us dou r with respect to y. We're partially differentiating it, so x is constant. Then we get minus 1 by y square. X is constant, so we leave it as it is, by dou u by dou s. We are partially differentiating this equation with respect to y, so that would give us 1 by z. This would be equation number 2. Similarly, dou u by dou z is going to be differentiate with this equation partially with respect to z, we get minus y by z square plus dou u by dou t. Differentiate this equation partially with respect to z, so x is constant. We get 1 by x. That's our third equation. Now equation 1 into x plus 2 into y plus 3 into z would give us x dou u by dou x plus y dou u by dou y plus z dou u by dou z. So this whole equation we're multiplying with respect to x. So this is gonna get x, we're gonna get another x over here, and another x over here. This x and this x get cancelled. So our terms are dou u by dou r x comma y x by y plus dou u by dou t minus z by x. Similarly, we are multiplying y on both sides, and we get dou u by dou r, we'll take minus outside, x by y square into y, so y and y get cancelled, there's our term, plus dou u by dou s into 1 y by z. And we're multiplying this whole equation with respect to z. That gives us minus dou u by dou s into y by z plus dou u by dou t into z by x. Now if you see dou u by dou r terms, this and this, they're both similar and in the opposite and have opposite signs, so these two get cancelled. Now take dou u by dou t terms, these two are same with opposite signs, so these two cancel as well, and dou u by dou s, same terms, different signs, so they cancel as well. So that gives us to 0. This is the equation we got, which is what we were supposed to prove.